We're going to talk about some more interference. Right now we're going to look at it specifically with light. We're going to talk about another wave quality called diffraction. It's through diffraction that we end up getting interference for light. Turns out, have you ever been at a beach where they have the breakers? Little ways away from shore, they have big cement blockades or rock blockades. So you have these big old waves coming in. It could be, yeah, semi-tires, something that's big and massive. So you have these big waves coming in from the ocean. When they hit these breakers, well, it stops some of the wave, but there is openings between the breakers, which allow some of the waves to come through. The waves, as they go through that opening, they end up spreading out through a hemisphere, or a semicircle, whichever way you want to look at it. And so it spreads the same wave over a much bigger area, which decreases the intensity. Because remember, intensity is power over area. If you can spread your wave over a bigger area, you're going to lessen the intensity. They have breakers at family-friendly beaches where you would take little kids to go swimming, for example, so that the big waves wouldn't be knocking the kids down. You obviously don't have breakers at a nice surfing beach because you want the big waves. Turns out all waves do this. All waves diffract. So as the waves come in, they get spread out. If they hit a boundary, they get spread out over a larger area. Light does the same thing. As light comes in, it gets spread over a much larger area. A couple ways we can draw it. We can draw the wavefront itself, and these lines would represent the peaks of the waves. Or we could draw arrows to represent the light rays, the direction that they're traveling. When they come out, they get diffracted in all directions. Turns out the smaller the opening, the bigger that diffraction is. The bigger the effects of diffraction are. The bigger the opening, the smaller the effects of diffraction. So what we're going to look at is we're going to look at light traveling through a couple different slits. Slit is simply a nice little opening for the light to pass through, and those slits will cause the light to diffract and go out in different directions. And so what happens, each light ray, there's millions of light rays coming through, but you end up with a whole bunch of them diffracting. So with all of these light rays diffracting, when we let them hit a screen, our screen in this case is going to be our whiteboard. When we let them hit a screen, depending upon how far the waves have traveled, they may interfere constructively or destructively. So I'm going to go a little out of order from your book. I'm going to start with a single slit diffraction pattern. A single slit is just like this, one little opening. So what I have is I have a little slide that has some vertical slits on it. The slits are very, very small, but they will cause the light to diffract. In this case, I just have a laser. The width of this slit is 0.04 millimeters. It's very, very tiny. The pattern we see with single slit interference is we get a wide bright spot. We call that the central maximum. Central because it's the one in the center. A maximum because it's bright. There's dark spots on either side. So there's a dark spot here and a dark spot here. Those are points of destructive interference. Perfect destructive interference. Okay? So we would call those minima or minimums. There's bright spots on either side. These would be the first maxima, the first one on either side of the central max. Then there's another dark spot. Then there's another bright spot. It's not as bright as the other ones, but it is still red. You still see the color of it. So this pattern is unique to the single slit interference. The slit that this is shining through is vertical. It's about maybe a centimeter tall, and then it's only 0.04 millimeters wide. The diffraction happens horizontally because that's the narrow portion. The slit is too tall for us to see diffraction vertically. It's too tall, so the diffraction is minimal. That's why we don't see the light spreading out vertically. If I change the width of the slit, so I'm going to slide this over. I'm going to be doubling the slit. So right now it's 0.04. This is 0.08. So the slit is twice as wide than it was before. Sorry, I'm blocking it. But notice the pattern, the overall shape of the pattern, there's still a wide, bright central maximum, and then smaller maxima on the other sides. This time now, the central maxima is smaller. Those are the two dark spots that surround the central maximum. As the slit gets bigger and bigger, the diffraction pattern gets smaller and smaller. Okay? I can double it one more time. So it's 0.08 millimeters right now. Now it's 0.16 millimeters. The wide, bright central maximum, and then the smaller maxima on the other side, this is characteristic of the single slit interference pattern. In terms of equations, we can write an equation that will allow us to describe where the dark spots are, where the minima are. Because the maxima are such a wide range, we don't tend to talk about the equations for constructive interference. We only look at equations for destructive interference. And destructive interference is very specifically located, and constructive is everywhere in between. Okay, so I'm going to draw as if we were looking down on the slit. We could see the slit from the top. The width of the slit, how wide it is, we use the symbol lowercase a to represent it. Now this is highly magnified, obviously. These slits were 0.04 millimeters is where we started. We ended at 0.16 millimeters. Over here is our screen, which in this case is the whiteboard. That's where we're seeing the interference pattern. I'm going to draw a reference line just to make things help us out a little bit. So my reference line is just a straight line from the middle of the slit straight to the board. It has a length, we're going to call the distance from the slit to the board L. So L is just how far away the slit is from the board. Now we know that there's a central maximum, the wide, bright spot. This is called the central maximum. You can easily figure out how wide it is if you can locate the positions of the first dark spots, so the first minima. The first minimum on either side is located the same distance from the center of the central max. So if you're to measure from the absolute center of the central max to the dark spot on one side versus the center of the central max to the dark spot on the other side, they're the same distance away. Okay? And then, of course, we get bright spots. They're not as wide nor as bright as the central max, but they are there. The next dark spot would be the second minimum, and so forth. So what we're looking at is we have light coming, make this simplistic for us. We have light coming from the top half of the slit and hitting this point. We have light coming from the bottom half of the slit and hitting this point. So let's look at light from the middle of the top half. Now there's tons of light coming through the entire slit. We're only going to draw 2 light rays. They're in no way representative of absolutely everything that's going through there. Okay. So this light has to travel that far to get there. I'm going to go from the middle of the bottom half to the same point. Now the light itself is all coming from the laser. It's all laser light. It's all in phase with each other as it leaves the laser. Going back to the last chapter, that means delta phi naught is 0. Okay, yeah.
So does this interference pattern only work with, like it's on phase?
You can get interference patterns if they're out of phase. It just would look different. But yeah, if you were capable of getting 2 lasers that were out of phase with each other shining through the same slit, yes, you could get some sort of different interference pattern. Okay, so delta phi naught is 0. These spots here that we're going to look at are destructive interference spots. Do you remember, for destructive interference, delta x was some multiple of a half a wavelength. That allowed us to get destructive interference. If the extra distance traveled was a half a wavelength, or 1.5 wavelengths, or 2.5 wavelengths, that shifted it by half a wavelength. That lined the peaks with the valleys. So we get destructive interference. They cancel each other out. This is going to apply here. This first minimum, m is going to be 0 in this equation. So we're going to get delta x, 1, the first one, is going to simply be 1/2 a wavelength. So what we need to do is figure out how much further the one wave traveled than the other. The orange one traveled farther to get to this point than the blue one did. We need to know how much farther. If I draw a line over, down perpendicular, that is our delta x, right there. I'm going to draw a blown up version. So if we could zoom in on this picture. The width of the slit is incredibly tiny. The distance to the screen is quite large. If we were to really focus in on just 2 of these light rays, they would look parallel to us at this point. And that's because A is so incredibly small compared to L. Okay? So the extra distance traveled, if I drew this line over, that's the extra distance the orange wave had to travel further than the blue wave did. Okay. This distance from here to here, since we drew light from the middle of the top half to light from the middle of the bottom half, they're half the width of the slit apart. So this distance is A over 2. If we put an angle in here, I'm going to put an angle and call that theta. Then just from right triangle geometry, or trigonometry I guess, the sine of theta will be delta x over the hypotenuse. So delta x will be A halves sine of theta. And that's just from the geometry of the problem. Now that theta is the same. If I were to draw a line here, starting in the middle, just from my reference line, up to the same point? That would be in the middle here. Here's my reference line. This angle is also theta. So from the horizontal up to this parallel line is the same as from the vertical to the perpendicular to have that parallel line. So theta is the same thing in these cases. We know, if coming over to this black triangle, we know this side is L. This side, the distance from the middle of the central maximum to this dark spot, let's go ahead and call that Y. Just meaning a vertical height, vertical distance. From this geometry, since we know this side is L, this side is Y, the opposite side versus the adjacent side, that would be tangent. The tangent of theta will be Y over L. So we get a few relationships that relate things together. First of all, let's relate. We know delta x is half a wavelength for this first dark spot, but we now know that delta x is also equal to a over 2 times the sine of theta. So let's equate these. The 2's cancel. So we get a sine of theta is equal to lambda. That's for the first minimum. A sine theta is equal to lambda. For the second minimum, n would equal 1. 1 1/2 is 3/2. So we're going to say A sine theta is equal to m lambda to represent all of those minima, all those dark spots. So that's our generic. Now, theta. Imagine drawing a line from that slit back there in the back of the room. One of them to the middle. So the middle of the central max is right there. So one line from that slit to here, and then one line from that slit to the first dark spot, which was here for our original setup. So 2 lines all the way starting back there, one of them pointing here, one of them pointing here. Will the angle between those 2 lines be very big? No. Theta, because try that again. A is so much smaller than L. Theta is really, really small. That means the hypotenuse of this black triangle is going to be pretty much L. Y is so small compared to L that the hypotenuse, if you did the Pythagorean theorem, that the hypotenuse is pretty much the same thing as L. So the sine of theta, Y over the hypotenuse, and the tangent of theta, Y over L, is pretty much the same thing. Sine of theta is pretty much the same thing as tangent of theta, which really is pretty much the same thing as theta in and of itself if you measured it in radians, if theta was in radians. What that allows us to do is to take this relationship, that's just from the geometry of the problem. The tangent of theta is Y over L. And to take this equation for our first dark spot, combine them together. Since the sine of theta and the tangent of theta are pretty much the same thing, I'm going to put Y over L in for sine. location of the first dark spot, measured from the middle of the central maximum. Please keep that in mind. The Y is measured from the middle of the central maximum. The location of the first dark spot depends upon the wavelength of the light you're using, depends upon how far away your slit is from your screen, and it depends upon how wide the slit is. Okay. What if you wanted to know how wide the central maximum was? So the width of the central max. Yeah. Just 2y1. The first minimum is y1 on either side of the central maximum. It doesn't matter which side. They're the same distance from the center of the central max. And so 2y1 will give you the width of the central max. Now, an application of this, whether you know it or not, you actually deal with this all the time. You have a slit, it's not a vertical slit, but you have a slit that you are looking through every single moment of your life. And it's your pupil. Your pupil is a slit. Your pupil is causing diffraction patterns on your retina. Okay? Now, they're not nice straight lines like this one. The vertical slit is what gave us the nice straight lines. With a pupil, with your circular opening, they call it a circular aperture. The pattern looks like this. Your central maximum is a circle. It's bright. Sorry, by filling it in, I'm trying to say that it's a bright spot, not a dark spot. So you get a bright bullseye. You get a dark spot around it. And then you get another pattern that's bright around it. And so forth. So it looks like a bullseye pattern. Okay, now we're not running around seeing bullseyes, obviously. But what happens, this concept is related to resolution. Have you ever seen those paintings that are a whole bunch of dots of color? You stand close enough and you can see all the individual dots, but you stand far enough away, it looks like a nice, normal, beautiful painting. It's called resolution. When the light is coming from those individual dots, if they both create individual circular patterns that don't overlap on your retina, then you see the individual dots. You can see each dot individually. If their patterns overlap, so you have one lying on top of the other, then your eye can't distinguish that there's two dots there. It smears together. It's the same concept as driving in the dark and you're watching the lights from the traffic in the other direction, and you wonder if you're seeing a motorcycle or a car. Because if they're far enough away, you can't tell if it's one headlight or two. The concept is called resolution. And it has to do with these patterns creating their own individual patterns on your retina. The equation, by the way, for the circular aperture is very slightly different than what we just derived for the single slit. So these equations, our slit was vertical, and the diffraction pattern was out horizontal. Here we get the minimum angle .22 lambda over d. The 1.22 is what makes it circular. I haven't driven the equation, so I'm not exactly sure which part of it makes it. But the 1.22 you see because of the circular opening. Lambda, again, is the wavelength of the light passing through the slit. D will be the diameter of the opening, so however big that slit is. Be it your pupil, or the same concept applies to telescopes, and to binoculars, and to microscopes. So D is the diameter of whatever is looking at it. This equation, still perfectly applicable. Okay? So you can plug in y over L for theta minimum. Y, again, will be measured from the center of the central maximum. So the center here, out to the middle of the dark spot. Okay. Questions so far? Please.
So this is more about the edges of the slit, right? Not so much.
Right, it's the fact, yes, it's due to the edges. When it reaches that boundary, it causes the light to diffract out. Yes.
Because I know that when I did studies, or when I was studying for the ham radio exam, they talk about radio signals getting diffracted off of like the edge of a building.
Yeah.
And it works the same way. We get that strong, weak, strong, strong, strong.
Exactly.
Diffraction.
Yeah, so any sort of boundary will cause the light to diffract and bend off. Exactly right. Yes?
Oh, okay, over here you have Y being half the distance of your central max.
Yes.
Over here, will it be a little bit more? Is there a difference, or?
No, it's still half the distance.
Okay.
Because it's from the center out to the dark spot. Now, are you meaning like a little bit more because of this?
Yeah.
Yeah. Even this one, even the single slit interference, there's still a little bit of a width to it. This is still to the middle of the dark spot. So there's a little bit of the fringe that's dark, yes. Okay, so single slit interference pattern. A wide, bright central maximum. Maxima on either side, they're not as bright, nor are they as wide. They're actually half as wide as the central maximum. The intensity decreases the further out we get. Okay, we're going to look at the double slit interference next. The reason I show you single slit first is because the double slit, it gets superimposed on the single. Okay, so to remind you, there's the single slit interference pattern. This particular slit has a width of 0.04 millimeters. I'm going to take a slide now where there's two slits. They're just side by side. They're both vertical slits. They're side by side with each other. They individually have slit widths of 0.04 millimeters, but they are a distance of 0.25 millimeters apart. Okay, so the width of the slit themselves is still 0.04. If you notice, we still have a central maximum. You still get the single slit interference pattern, whether you want to or not. And that's because there are two single slits. Nothing we can do about that. What is different, though, is our central maximum is no longer a nice, bright, straight line. We have a bunch of individual bright spots and dark spots. Turns out they're all equally spaced from each other. The distance from a dark spot to a dark spot is the same as the distance from a bright spot to a bright spot. So with double slits, you get equally spaced interference. You get alternating bright and dark spots. So the bright spots are maximums. The dark spots are minimums. Okay? This equation is still perfectly valid. We need to modify our picture ever so slightly. There's now a block right there. There's two slits. Each of these slits has its own width of A. The distance from center to center of the slits now is called D, little d. So little d is the distance from the center of one slit to the center of the other slit. Now we have light coming from one slit and light coming from the other slit, traveling along, coming up, and hitting the whiteboard, our screen. Our pattern, though, is we get equally spaced bright and dark spots. So the pattern looks a little bit different. This is still true for destructive interference, because this is still true. The light is still in phase. It's all coming from the same laser. So this equation still describes the destructive interference. We can easily talk about constructive interference as well now. They're all easily found. Delta x will be m lambda for constructive interference. Our extra distance is now d sine theta, for the same reason it was a over 2 sine theta before. All we've changed is what we're calling that distance from one light ray to the other. So we can say d sine theta is equal to m lambda for constructive interference. We can say d sine theta is equal to m plus 1/2 lambda for destructive interference. Okay. M can start at 0. If m is 0 here, that just means that there was no extra distance traveled. So what point on the screen would that refer to?
Central mass.
The center. Exactly. The absolute center would be m equals 0. M equals 0 for destructive would be the first dark spot on either side of that center one. M equals 1 will be the next dark spot on either side. And so forth. Same geometry in the problem, so this equation is still perfectly applicable. Now again, if you imagine drawing a line from that slit to the center, and from that slit to whichever spot you're interested in, our angle is going to be really, really small. We can modify that ever so slightly. Because D is so much smaller than L, our angle is really, really small. The sine of theta and the tangent of theta are the same thing, which is also the same thing as theta in and of itself. So you can write these equations as theta would be m lambda over d if you want. Plugging in y over L, this is constructive. So the constructive interference points, y still is measured from the absolute center of the center spot, bright spot. So y is from the center to whichever spot you're interested in. Lambda is your wavelength of the light, so our laser in this case. L, still the distance from the slits to the screen. D is how far apart the slits are. If we plug y over L in this equation, y for destructive looks very similar. We just get the m plus 1/2 term rather than just the m term. So these equations allow us to easily figure out where the y is, or you could experimentally measure the y and work backwards to find d, your wavelength, whatever it is you happen to be looking for. If I had a different color laser, this one's red. Red is on the high end of wavelengths. Remember, visible light's between 400 and 700. 700 end is your red end. What would happen if we used a different color, say green? what would happen to the pattern?
Smaller.
Get smaller. Wavelength of green is smaller than the red light. If our numerator gets smaller, then y gets smaller. So we would still have equally spaced dots, but they would be closer together. So with the bright, dark, would all be closer together.